Okay, so this is chapter 2, question 2.15. There is a turtle that crawls along a straight line called the x-axis, positive direction to the right. The equation for the turtle's position as a function of time is x of t is equal to 50 plus 2t minus 0.0625 t squared. In part A, we're supposed to find the turtle's initial velocity, initial position, and initial acceleration. What I want to do is I want to write the position function. So the position function um, is the function that they gave us, which is x of t is equal to 50 plus 2t and then minus 0.0625 t squared. And we're supposed to find three things: initial velocity, initial position, and initial acceleration. If we want to start off with the initial position, that would be easy to find using the position function. The position function literally tells you what your position is at any given time. Um, Therefore, if you want to find something like the initial position using the position function, you should just remember that the initial position implies that time would be zero because initial means it's at the beginning, and beginning would mean that, well, the time would be zero because that would be the beginning. So if we want to know where this turtle is at time equals zero, we plug in t equals zero into the position function. So the position function evaluated at a time of zero would be 50 plus 2 times 0 minus 0.0625 times 0 squared. Obviously, this piece in here goes to 0. This piece in here goes to 0. So you just get 50, which means that the initial position of this turtle at time equals 0 would be at 50. The units are in centimeters, so it would just be 50 centimeters is our answer for the initial position. The next question that we have in part A is we need to find the initial velocity and the initial acceleration. If we wanted to, let's say, focus on the initial velocity, we'd need to know the velocity function. So let me just write this out, the velocity function. What we know about the velocity function is that it's actually the first derivative of the position function. So what we will do is we will take a moment to um, focus on the original position function, and we're going to take the first derivative of the position function, and that'll give us the velocity function. So what I'm doing right here, just writing down some notes for myself, is I'm taking the first derivative of the position function, and then the function that I get from that, I'll call the velocity function because the velocity function is the first derivative of the position function. And if we took the first derivative of the position function, notice that this 50, because it's a constant term, would go to 0. And if we took the first derivative, this term 2t would become 2. And then this term here is, you'd have to use the power rule on it. The 2 goes in front to multiply against the negative 0.0625. And then this t is still going to be there after we take the derivative, but its power is not going to be 2. This 2 is going to go down 1, become a power of 1. So that'll be t to the first power, or just t. Okay, so let's write all that out. There was a lot. As I said, the 50 goes away. 2t becomes 2. And then we multiply 2 times the negative 0.0625. That'll give us negative 0.125. Hopefully I did that right. And then there's going to be a t afterwards. That is now our velocity function. I'm going to highlight this in green so that way we now have that in mind as our velocity function in case we need to use it later. And the question in here was asking, okay, what was the initial velocity? Of course, initial velocity implies that, just like initial position is time 0, initial velocity is the velocity at time 0. So in our velocity function, we would evaluate that at time 0, which means that I would go v of 0 and then just plug in 0 wherever I see t. That'll be 2 minus 0.125 times 0. Of course, this part goes to 0, so I just get 2. The units for our velocity would be centimeters per second. So that would be 2 centimeters per second for our initial velocity. And in part A, we needed to find a third thing, which was the initial acceleration. Obviously, if we're going to work on initial acceleration, we need to know our acceleration function. So let me just write that out here. Acceleration function. Now, the acceleration function is defined as the second derivative of the position function. So I could write that out using the language of calculus as x double prime of t. And if you just apply a little bit of logic, you'll realize that the second derivative of the position function is also the same thing as the first derivative of the velocity function, because the velocity function is already the first derivative of the position function. So if you take the derivative of that, when you take the first derivative of the velocity function, you're really taking the second derivative, getting the second derivative of the position function. So second derivative of the position function is the same thing as the first derivative of the velocity function, which is technically just a fancy way of describing my acceleration function, which I'll call a of t. And to get a of t, we have to take the first derivative of the velocity function. Our velocity function is in green. It's 2 minus 0.125 t. If we took the derivative of that function, this 2 goes to 0 because it's a constant term. And then this negative 0.125 t just becomes negative 0.125 because this t goes away when you take the derivative of this term. So what we can conclude about this is that our acceleration function is just this negative 0.125. Let me highlight that in blue, I guess. I don't know what color I want to use for this. So our acceleration function is this. What this means is that no matter what time it is, the acceleration is always going to be the same. It's negative 0.125. The units for that would be in centimeters per second squared. So, and I just want to move this down a little bit so that I stay neat. I'm just going to move this down just a little bit. Therefore, we can just, to wrap that part up, we could say that our initial acceleration, which obviously is the acceleration at time 0, is going to be negative 0.125. So it's negative 0.125 centimeters per second squared. That's the units for acceleration. Okay, so we're done with part A. Part B says, at what time t is the velocity of the turtle? 0. Okay, so let's see if I have enough space for this. I'll write it up over here. So we're doing part B now. We want to find the time when the velocity of the turtle is 0. Okay, so obviously we have to work with the velocity function here. And what I want to do is let's just put that right here. And that's our velocity function, and we're going to figure out the time that makes the velocity function give you 0. So let me just delete this part here. We don't need that. and then we take the velocity function and we set it to 0, and then we solve for time. When we do a little bit of algebra, we'll add 0.125t to both sides, so you'll get 2 is equal to 0.125t. And then you'd want to divide both sides by 0.125. I think 2 divided by 0.125 is 16. Let me just double check on my calculator. Yeah. So there we get t is equal to 16. And our answer is that, if we're looking for the time when the velocity is 0, the answer to that is at 16 seconds, the velocity will be of this turtle will be 0. Okay, so we're done with that part. In part C, it says, how long after starting does it take the turtle to return to its starting point? Now, this is a tricky question because the starting point is not actually at 0 like it is in most problems. The starting point would be, I think, the initial position, which is at 50 centimeters. So when they say return to starting point, really they want to know when the turtle comes back to the position of 50 centimeters. That's what I think is happening. So let's see. In part C, what I'm going to do is I'm going to start with copying the position function. We need that. And what we want to do is we want to set it equal to 50 and then solve for the time that would make that 50. So you've got now an equation that says 50 plus 2t minus 0.0625t squared is equal to 50. If you do a little bit of algebra, you'll notice that the 50s could be canceled on both sides, leaving a 0 on the right side. And then I think what we could do next is we could factor out a t on the terms on the left side of the equation so that you'd get t times parentheses 2 minus 0.0625t is equal to 0. And this is one of those quadratic style equations where there's going to be two solutions. You just need this one to become 0 and this one to become 0 in order for you to get those the two solutions. Obviously, the first one, t, the only way to get that to 0 is if t is 0 itself. So that's an easy answer from here. This one, the 2 minus 0.0625t, the way that you could figure out how it becomes 0 is you set it to 0 and solve. So I have 2 minus 0.0625, t is equal to 0. We'd add 0.0625t to both sides to get 2 is equal to 0.0625t. Then we divide both sides by 0.0625. So you'd get 2 divided by 0.0625. Just doing that on my calculator, I get 32. So what we see from here is that the turtle is at the position, the start position of 50 centimeters at 2 time points. It's at the time point when time is 0, which is basically at the beginning. And then the second time that it is back at that start point of 50 centimeters is 32 seconds later. So at 32 seconds, the turtle is back at the start point. So I think our answer for part C, which is how long after starting does it take the turtle to return back to its start point, the answer to that is going to be 32 seconds. At 32 seconds after the time 0, the turtle is back to the position of 50 centimeters, which is the same as what it started off with. Okay, so let's go on to part D. Part D says, at what times t is the turtle a distance of 10 centimeters from its start point? And what is the velocity of the turtle at each of these times? This is a bit of a confusing question. I'm going to actually erase some stuff to make some space here. So I'm going to erase this just to make some space. So this is a confusing question. It's asking about when it is a distance of 10 centimeters from the start point. The start point is at 50 centimeters. And a distance of 10 centimeters from the start point would be like, if I added 10 to 50, that would be at 60 centimeters. And I guess the way to approach this in part D is to focus on the idea that you need to find the times when the turtle is 10 centimeters away from the start point. And if we focus on that key idea, 10 centimeters away from the start point, and the start point being like 50 centimeters. So the start point is 50 centimeters. 10 centimeters away from the start point could either be at 60 centimeters from the origin or at 40 centimeters from the origin. So we have to, I think, solve for the times when the turtle is at 40 centimeters away from the origin, as in like the origin of the coordinates, not the start point. The start point is at 50 centimeters away from the origin. Um, and then also like when the turtle is 60 centimeters away from the origin. That because at 60 centimeters away from the origin, that would mean that the turtle is 10 centimeters away from its start point. So we need to know the times for when the turtle is at that position as well. So what does that mean? Well, it looks like we're playing around with the position function again. So we're going to take this little guy, the position function here, and use it to help us solve our problem. For the first one, I guess what we would do is we would want to set this equal to 40 and solve it. And then hopefully that'll give us some times. That will work. What else? Then, separately, what we would do is we would take that same position function there and set it equal to 60 and then solve it. And then it'll give us some more times when this turtle is 10 centimeters away from the start point. And, solving these might actually involve using the quadratic formula. But what I'm going to do to make life easier is I'm going to use graphing methods to solve for it. So for the first one, if I subtracted 40 from both sides and rearranged it, that would look like negative 0.0625 t squared plus 2t and then plus 10 is equal to 0. I could graph that, and I just want to know when it crosses the x-axis because that's when it would be 0, and then that would give me some times. That would be the solution for this. So let's put that in here. 0.0625 x squared plus 2x plus 10. That gives me a parabola. Notice that this parabola is at 0 at a negative time frame, and then also, which I'm not going to use because I don't want to use the negative time. It doesn't make sense. But it gives me this interesting answer at 36.396 seconds. So I'll call it 36.40. That means then that my solution in here is at 36.4 seconds at t equals 36.4 seconds. The turtle is 10 centimeters away from the start point. In fact, it's at 40 centimeters, which is 10 centimeters away from the original start point of 50 centimeters. Okay, so that's one solution. The next solution that we want to work on is the second parabola here, which is 50 plus 2t minus 0.0625 t squared equals 60. If I subtract 60 from both sides just to make my life a little easier, let me do that that out first. I will get a new equation that looks like negative 0.0625 t squared plus 2t minus 10 equals 0. And I could solve that, or I could graph that and see where it crosses the x-axis. Negative 0.0625, 2t, and then minus 10. And then I graph that. And it looks like it crosses at two spots here. Let me just zoom in a little bit. It crosses at two spots here at 6.2 seconds and at 25.8 seconds. So I have two more answers here. At t equals 6.2 seconds and at t is equal to 25.8 seconds, the turtle happens to also be 10 centimeters away from the start point. But at these times, the turtle is at 60 centimeters, which is 10 centimeters away from the start point of 50 centimeters. Wow. So I've got three answers to part D. And then if I go back to the question, it says, at what times t is the turtle a distance of 10 centimeters from the start point? We found three times like that, which were 6.2, 25.8, and 36.4 seconds. And now it says, what is the velocity, magnitude, and direction of the turtle at each of these times? Okay, so if we want to know the velocity, we basically need to focus on the velocity function here and plug in this time into this velocity function to figure out the velocity at that particular time. And then for this time, plug it into this velocity function to figure out the velocity at that time. And then in here, we plug in this time into this velocity function to figure out the velocity at that time. Let's use our calculator here. Our function is v of t. Let's see if this will work. V of t, that's our velocity function, is equal to 2 minus 0.125 t. And now we can evaluate this function using the power of Desmos for v of 36.4, for t of 36.4. So we can find out the velocity there. Desmos says that the velocity is negative 2.55. So it's a negative velocity, and it's 2.55 centimeters per second. So in here, at this time, oops, did I want to do that? No, I didn't want to do that. At this time here, the velocity would be equal to negative 2.55 centimeters per second. That's at this time here. Then at 6.2 seconds, let's see what the calculation tells us. So at 6.2 seconds, oops, 0.2, it looks like the velocity is a positive 1.225, so it's moving to the right. If it's negative, it would be moving to the left, but it's positive, so it's moving to the right. So the velocity at 6.222 seconds, it would be 1.225 centimeters per second. So it's moving to the right. And then finally, we would do, okay, we would plug in V of 25.8, and we'd get negative 1.225 there. So it's moving to the left at a speed of negative 1.225 centimeters per second at that time frame. Okay, so we're done, I think, with part D. And part E says, sketch graphs of v x versus t, velocity in the x direction versus t, acceleration in the x direction versus t for the time interval from 0 to 40. Okay, well, that's basically graphing the position, velocity, and acceleration functions. So let's do that. I'm going to use a calculator here. The position function x of t is equal to 50 plus 2t minus 0.0625 t squared. So, this Desmos isn't doing a great job of graphing that, so I'm going to have to change it to look like this so it'll graph properly. Okay, so that's the position function. And if I wanted to limit it to between 0 and 40 seconds, the graph would more specifically look like, let's see, 0. So that's what the graph would look like on 0 to 40. And then the velocity function would just be 2 minus 0.125, 0.125 x. And then I'm going to introduce the same limitation there. So this is the velocity function. And then the acceleration function is just I'll have to graph it like this. And I have to limit it to the time frame that we wanted. There we go. So those are our three functions from 0 to 40 seconds. Okay. And I think we're done with that problem.